Hello everyone. Let's start the class. So I am Sourabh Deoghare, a PhD student at Sheffield. I work in the area of machine translation, and that's the topic of discussion for the day. So this will be the outline of the talk. We will start with the introduction of the problem. Then we will get a brief overview of two popular paradigms of MT, that is SMT and NMT, statistical machine translation, which was a precursor to uh, the deep learning era that started after 2014. And since deep learning, the entire focus of the field has shifted to neural machine translation systems as opposed to statistical ones. We will also look at the aspect which is important while developing the MT systems, that is evaluation of these systems. So we will quickly touch on the human side of evaluation and also the automatic side. Furthermore, at a high level, we have discussed two sub-problems in the field of machine translation. One is automatic post editing and other is quality estimation. These problems are uh, these things are post processors of after the MT problem. And we will also finally see how we can use the automatic post editing systems and quality estimation systems to improve the NMT or SMT models. So, starting with what is MT, so machine translation is a problem where we want to develop a computer system or a program to translate text given in one language to the text given in another. As shown here in the diagram, we have an English sentence. So we have a source text here and in English, and we pass it to a empty system, and what we get is the translation in the language of our interest. So it is called as target text. So why do we need machine translation? A one-line answer would be we want to mitigate or reduce the language barrier, and we want to access and interpret and understand the information which is in one language in our own language. So who needs it? If you think about it, the translation is required by pretty much everyone. The government needs to translate all its administrative documents like notices and all, which are essentially in English or Hindi, and then they want to translate it in all other languages. If you think of the judiciary, then mostly the lower courts, they mostly operate in the regional languages, and then high courts and supreme courts also have the value of these cases. So entire all case proceedings needs to be translated to English or Hindi language, which are the official languages for the processing of the higher courts. Like I can go on and count the applications. There are many. Like here I have mentioned some domains where in entertainment we can see subtitling is required in other languages. In education, obviously we would like to access the content which is not available in, let's say, English or Hindi in these languages to learn and so on. So also even in a country like India where there are multiple languages, even normal people, tourists, they also need the translation services when they visit other states for convenient of clear communication. So yeah, so that was the side of application of MT, why the world cares about it. But as a CSE people, why do we care about it? Why is this problem interesting to us? I have just listed some of the major reasons. So if you look at any multilingual NLP system, multilingual text summarizer, multilingual paraphraser, and whatever, uh, it has multilinguality in some sense, and under the hood, there is a need to use the machine translation essentially, or techniques or different hacks from MT into them. The problem is very old. The problem is actually as old as the computers. World War II was something that demanded the need of machine translation systems. So you can imagine the people have been working on this problem from that era, and still so we have made a really good progress, but we are not where we would like to be. So that problem keeps fascinating researchers. This is one of the problem that falls at the intersection of two major aspects of NLP, natural language understanding and natural language generation. So we need to analyze the text that we want to deal with, and then that is not enough. Interpreting that text is not enough, but we have to go to the other language and then generate a corresponding text. So generation capabilities are also necessary. And if you have been looking at recent papers in different areas, you can see the techniques which were initially proposed in the machine translation field have been borrowed to solve other problems like ASR, TTS, or even any range of problems like in majorly in time series data tasks and so on. So these are some of the reasons why we are interested in. Now, why is this problem so difficult? If it is a very old problem, there was a huge demand for this for the empty systems. What is stopping us from solving this? So the one answer that we can give for any question in NLP why this problem is not solvable, the one word answer to it is this ambiguity. We are dealing with not one but now more than one natural languages, and as you know, the natural languages are ambiguous for various reasons, like different languages have different syntactic semantic properties. Their word order could be different. One word may have multiple meanings depending on the context and so on. Also, there could be different ways in which how the language uses the prefixes and suffixes to convey meaning of a word in a certain context. So, what does a machine translation system essentially do is it deals with the language divergence. Language divergence means the difference in the way the language represents or expresses the meaning. So, majorly we can divide these divergences into two types. One is syntactic divergence, which arises due to the way the languages or the sentences or constructions in the languages are, they follow different structures. Or the other type is lexical semantic divergence that is so this caters to the differences that arises due to differences in the semantic properties of the languages. So we will see some of them first in order to understand what the empty system has to deal with while performing the translation. So first one, the simple one is the constituent order divergence. This arises due to change in the way the word order of the languages. So if you look at the English example here, uh, uh, so we can see English follows subject, verb, object, word order, while in Hindi it changes to uh, subject, object, and verb. So this change in the way the languages are, the word order is, that causes this constituent order divergence. So when translating, the empty system has to take care of it and do the reordering apart from just translating the segments of the translation, which would be words or phrases. The other type of divergence that we see under syntactic divergence is adjunction divergence. Adjunction divergence arises when we have a noun, head noun, and there is a noun phrase or appositive, which whose placement can change depending on which language we are working with. Not so. This is just one example. Actually, this adjunction divergence arises whenever there is a change in the modifier, change in the placement of modifier. So here we have example Delhi, the capital of India, and then the sentence continues. But if we go in Hindi, we see the phrase capital of India, which is a positive, has translated first and has been placed first, Bharat ki Rajdhani, and then the head noun is there, that is Delhi. So this is adjunction divergence that we often see in English Hindi pair, and depending on the language pair, these may change. We have one more example here. I am going, and in Hindi, its translation is ja raha hu. So if you see here, the word I doesn't get mapped to any of the words in the Hindi. So there is no one-to-one correspondence or one-to-many or many-to-one correspondence at all. Rather, it is one-to-null correspondence. So some languages allow us to omit the subject in the sentence under certain context, and which we can see Hindi does it, and but English doesn't. So there is this null subject divergence in English Hindi pair. So these were some types of divergences that arises due to structures of the sentences. Now let's go to the semantics. So we have one example here. First example here is of conflectional divergence. The sentence is he stabbed him, and in Hindi we have उसने उसे छुरे से मारा. Now look at the word stab in English. Here it has come as a verb. But if you go to Hindi, stab is translated as छुरे से मारा. So there is a noun and then there is a verb. So it's a noun verb phrase. So verb has been translated to noun verb phrase. So this is called as conflectional divergence. Another divergence that we see is categorical divergence. So the example here we have is they are competing. वो प्रतिस्पर्धा कर रहे हैं. So here you can see competing has completely, so it is again, it is a verb here, but it has translated to Pratispardha, noun in the target language, and then we have additional verb to complete the sentence. So do, like if as if there is a word do in the English, which is translated to, or doing, which is translated to kar rahe. Another type of divergence that we see is head swapping diversion. It could be either emotional or demotional, depending on whether syntactic constituent of the sentence, whether its POS position has been promoted or demoted. So here we have an example, the play is on. Now, if you again look at the word on, here it is the logical modifier in this example. It is an adverbial in this particular sentence. Now, if you see the translation, we cannot translate it as khel, maybe something on car translation, and then we are just done with it. No, that cannot be done. So if we see the translation, it is khel chal raha hai. Now. So on doesn't really mean chal raha hai, but in this context it is it means it. So adverbial has been promoted here, and the translation we are seeing is chal raha hai for on. So these are certain things that MT system needs to take care of when performing the translation. So people have tried to take care of these things at different in different ways. What came up after some work is this vacuous triangle. Here we can see we have a source sentence on left side and we have a target sentence on the right side. And we can analyze this source text at different layer of NLP. So we can perform morphological analysis, syntactical analysis, semantic analysis, and so on, depending on the target language and also the source language. If two languages are very similar, let's say there is just one-to-one correspondence between the source and target language words, in that case, we are very well off with the morphological transfer. We just have to have a way to know, given a word, what is the translation in other language. So depending on the complexities involved and properties of source and target languages, this approach is followed. So analysis is performed at certain level, and then generation is performed at certain level. So as we can see, as we go up the towards upwards, we see the complexity keeps getting increases. And on the top, what we have here is interlingua. Interlingua, so there was an idea that to do this, that let's take all the languages in the world and generate a common representation for all sentences or words in all the languages. And then whenever we want to perform translation from any language to any other language, we can just refer to this common universal representation and then go to the other language. But it was pretty much difficult to do it. After a few years, finally the effort was dropped and they moved to again transfer-based translations. So then the question now comes, so we are not getting into details, but still just to give an idea, why these different types of transfers are needed, why we cannot always go with just morphological or syntactic or any other transfer. So here are some examples. For English Hindi, so here is a sentence, I am eating an apple, and the translation if I go at word order, would be मैं हूँ खा रहा एक सेब, okay, which is not correct. We need to understand the syntax here in order to translate this sentence correctly. So we need to move to the syntactic transfer, at least for this sentence. But is that enough? Here is another example. So the example is I miss the bus every day. And if we only care about the syntax and we can see the fluency improves, that means the sentence is fluent in the target language, but is it representing or conveying the exact meaning that was conveyed by the source? No, because the miss has been used in another sense. That means now we need the semantic understanding to perform this transfer. Here we have another example at the semantic level transfer to see whether we can always blindly trust semantic level transfer and develop empty systems, which we hope perform good. So here is an example. His departure was for good. Now you see all words are translated correctly, and also the sentence is also fluent and it makes sense in the target language. But here there is a hidden meaning or underlying meaning of this phrase was for good in this context is different. So the model needs to have some extra understanding of the language in order to correctly translate this sentence to something like उनका प्रस्थान सदा के लिए था. So for these kind of difficulties, just going with certain transfers and saying, okay, for this language where we can go with this is not very straightforward. So based on this philosophy of vacuum triangle, different approaches were developed. We are just going to go through them very quickly. So the initial ones were rule-based and knowledge-based empty systems. So they actually used linguists who knew both the languages, source and target, and asked them to write rules to perform to perform the translation. So they had to write more than even lakhs of rules, and yet it was observed that the empty systems don't perform that. So by this you can understand lakhs of rules means you would really need a quite extensive amount of resources in terms of money, human and time as well. Another problem with these were highly complex. Tuning them was not easy. If you have written 1 lakh or even 1 lakh is a very small number, if you have written 1 lakh rules, and then if you come to know, okay, this rule was wrong, then you have to go and make a change, and you also need to change the rules which were dependent on it. So doing this was a very difficult thing. So adaptation of these systems was pretty much difficult. Whenever we move from one domain to another, let's say I developed a rule-based system for medical domain, and then I'm translating the educational documents of CSE field with that system. That system is not going to perform well. Or another example could be I created a rule-based system to translate administrative documents, and then I am using that system to translate conversations of people, which are informal. So there are going to be so many differences that these systems won't perform good, and adapting them is going to be very costly. So here we can, as I discussed, there could be two kinds of systems. One is interlingua, which goes to a common representation and then goes to other side, and either it could be, or it could be a transfer-based system where we perform analysis at certain level, and then for generation we use certain level of analysis in target language and generate the sentence finally. People eventually shifted towards the data-driven system, data-driven MT approaches. These data-driven MT approaches need data, as the name says. So the data here, we are referring to the collection of sentence pairs, where in each sentence pair, there is one sentence from source language and its correct translation in the target language. First approach, which not really just a data-driven approach, which is partly rule-based and partly data-driven, is the example-based. So they rely on the data store, but they also rely on the analysis of the target language while generating the translations. That means they rely on rules for generation in the target language. While these next two approaches, statistical MT and neural machine translation, they are completely data driven, theoretically, but again, we have seen that if you incorporate linguistic knowledge into these systems, you can gain further performance, further improvements. Uh, yeah, so statistical MT was something that ruled the field for over 2 decades. So it was the precursor of NMT till 2014, after which the NMT has taken up. So this diagram shows how the trade-off between the need of data performance and the human effort. So these RBMT and DBMT systems, they don't need much data, but they need a lot of human effort to develop. Uh, while if you move towards the right side, you can see these SMT and NMT systems require less human effort, but more and more data. So here we expect these SMT and NMT, that means data-driven MT approaches, to learn the rules from data directly without human intervening. So with this, we are now going to spend some time with statistical machine translation. We are going to take a very high level view of it without going into the details. So how SMT, like statistical approach to MT, looks at this problem. So goal here is this, that we have a foreign sentence F, and we want to translate that sentence into English. The sentence would be E. We to do this task, we use a probabilistic model. Now why do we go for probability based model? For these reasons, we would like to have a measure of confidence for the translations that we learn using this model. So we would like to know what is, so like I should have an idea how good or bad or how less or more confident my system is if I want to end up using this translation somewhere. Also, there is a lot of uncertainty in the data because we are dealing with natural languages. And then probabilistic models are a natural choice to deal with the uncertainty. So these are the major reasons. So this will be the notations as we go forward. The source language, which is the foreign language, we refer it as F. The target language is English. The language is denoted with capital E, and the sentence in this target or foreign language is denoted as F, and E, English source sentence, is denoted with small e. What we essentially want to do here is then we would like to maximize the probability of getting the sentence E given the sentence F, if like for translating F sentence into English. Now, how do we go about it? So to do it, to compute this probability and get the translation E, we use the noisy channel, which is a general framework in range of NLP tasks. So how noisy channel modeling sees the process of this translation is, it looks at it as a process of recovering the original sentence given the target, given the corrupted sentence. So we are doing the opposite thing here now. So the advantage of doing this is, if we like we can use we can decompose the conditional probability of E given F into probability of foreign sentence given the corrupted or the original sentence English. And then this is something that we get benefited by this approach, apart from mathematical benefits, is that now we can model we can model this part of learning the probability of English sentences, which we are interested in generating separately. So we can call it a language model. So probability of E is the our language model, and this probability of F given E, is our translation model. So with noisy channel modeling, we have divided the task into translation modeling and language modeling. So what we do, we generate E using the language model. We pass E, that means the generated English sentence, through this noisy channel, and then we get the F using the corrupted version of this E, which we pass through the channel. Right. So so we can now connect these two probabilities with adequacy and fluency as well. Fluency means how fluent or natural the sentence is in that language. Adequacy means how well it reflects the meaning, or how faithful it is, how much we can trust that sentence to be the translation of the original source sentence. So translation model lets us work on the adequacy side, and the language model lets us work on the fluency side of the English sentences. Okay, I pretty much explained this. So yeah, so now what do we need to develop these language and translation models? For language model, all we need is monolingual data of that language. Again, that is one more advantage that we have here. We wanted to generate English sentences. All we have to do is just get English data. It could be anything. We don't have to care whether we have the translations of those English sentences into other language. And if we have just this monolingual data, we can learn the probability of E, and we have the language model. Now about but for this translation model, what we need is the bilingual data, or which is called as parallel corpus, which I explained earlier. A collection of sentence pairs where we have in each tuple, we have a source and target sentences. So the way we do this noisy channel modeling is a generative process. So we go step by step, as I explained already. So we generate E with probability E, then pass the English sentence through the noisy channel to get the foreign language sentence using the translation model, and then so we get the probability for it using the translation model, and finally we perform decoding to get the final translation. So before going to the translation model, let's quickly see how we can develop the language model. So we have the sentence E, we want to compute its probability, that is language model. So we can, like what sentence is made up of words. So let's say we have a sentence E with L words in it, even it to up to EL. How we can compute the probability using chain rule is we can just compute the probability of each word. So probability of first word would be just simple probability of it, or we can theoretically like condition it on the null. And then probability of next words in the sentences would be the probability of that word given all earlier words. The problem with this is, as we move ahead in the sentence, getting these probabilities, you would need a really huge amount of data, and even that may be less. So theoretically, we will need infinite data to get a good language model. So we use the Markov assumption that, then we use Markov assumption saying to get probability of next state or next word in this case, all we need is the current word, or whatever small window that we choose at current time. We don't have to care about what was there in the past. So with that, we can work with different n-gram models. So 1-gram model is the model that works on the words. So here the constituent here is the single word. If we say bigram model, so it's n value of n is 2, then it's a bigram model. Then for us, the basic unit to work with is 2 consecutive words. If it is 3, then a phrase containing 3 consecutive words, and so on. So here is an example. If we choose n to be 2, it's a bigram language model, and this is the sentence I'm discussing statistical empty. Then this is how I compute the probability. I given start or null, whatever we can put. So, but for next words, I always condition only on the one that means current words. If it was trigram, I would condition it on 2 current words, and so on. So that is it. That is the language model at a very high level. And then how do we get the translation model? That means how do we learn these probabilities? Probability of F given E. So to learn the probability for the foreign sentence given English sentence, we first need to learn the word level translation probabilities between two languages. So let's say we have English sentence again with L words, E1 to EL, and we have a foreign sentence with some M words, F1 to FM. Now, How do we use parallel corpus for this? Is we care about the co-occurrence. Let's say you have this parallel corpus. Assume that you don't know these languages. You can just see. What analysis you can do or how you can use this information is you can look at some words in these sentences and see which words frequently co-occur together in these sentence pairs. So if the two words co-occur with a high count, that means the higher probability of F given E. Right. So this is what we are going to compute. But before going there, here is something that we additionally need. So here is a sentence in English and in Hindi. The problem here is the point that we have to take care of is that the possibility of one source word getting mapped to different words in the target language, depending on what the sentence is. The word bank has two meanings. Bank is financial institution, and bank is also a river bank. So depending on the context, a same source word may get mapped to different words, and these words could also be present in the translation at different positions. So what can we do to learn these word translation probabilities in a better way? What if we learn the alignment probabilities also? What if we learn the alignments? What if I learn that in this sentence, the word professor gets mapped to professor. So the first word in the sentence gets mapped to first word in the target language, and so on. So if I have these probabilities, my confidence increases, and with this information, I can also learn the word translation probabilities in a better way. So now I have introduced, like, we have one more thing to take care of, that is alignment probabilities. So this is a function, or this is a set with alignments from source sentence to target sentence. Yeah, so given a source sentence and its translation, now our problem is to find these alignments. That means learning the edges here, knowing these edges. So now again, how do we, so yeah, so this is now extra thing that we have apart from our original English and foreign language, that means Hindi data in this case. So as I said, alignment A is a set where AJ belongs to these numbers, and we learn a mapping from mapping of alignments or these positions from source language to target. And how do we do it is a question. So again, there will be multiple possible alignments. If you look at the data, same word may get mapped to different, same source word may get mapped to different words at different positions. More important here is different positions. Uh, so it's obvious that if I have only single sentence pair, I cannot learn the word like these word alignments. But if I have multiple sentence pairs and alignments between the source and targets of those sentence pairs, I can learn these word alignments. So how do we do it? So here the word alignment is nothing but co-occurrence of these two words in whatever data that we have. So co-occurrence of foreign word and English word, the count of it divided by the co-occurrence of the source word, that means English word, and any other word in the corpus. So that is star and he. So E. So this count gives us the alignment probability or word alignment mapping for these words. Here is just one example of two, because here we have these two examples. The word prof is always mapped to prof here. So it gives the count as one for prof alignment. So now the issue is this. So so if you look at this, to get the word alignment, we need the translation word mappings or translation probabilities. And we said earlier that to learn the translation probabilities, we are going to use the word alignment. So it's like how to learn these two things which are dependent on each other, right? So see, so yeah, I have just mentioned the issue here. So we can find the best alignment only if we have the word level translation probabilities for all words, and we can get the best alignment. So also the best alignment is the one that maximizes the sentence translation probability. That means we need to know the word level translation probabilities and the best alignment as well. So now these are the two things that are interdependent, even though it is shown as a single way pointed arrow. So then how do we do it? So for that, what we use is an technique or algorithm called as expectation maximization. So we start by randomly initializing the word translation probabilities using our corpus, and then we perform this iterative two-step process. In the first step, we estimate the alignment probabilities using the word translation probabilities that we have. And in the next step, we use these estimated word translation probabilities to re-estimate uh, the word translation probabilities using new counts for the word alignments. Since we don't already know the best alignment, we consider all alignments, all possible alignments while estimating word translation probabilities. And also, instead of taking the best alignment, we consider all alignments and weigh the word alignments with the alignment probabilities that we just counted based on the recently updated uh, word translation probabilities as shown in the uh, slide. So here is a quick example of it. We are not going to go into the details of this algorithm, but here is an example. So let's say we are at some point of time in this iterative process. We keep iterating over steps 1 and 2 until we converge. So let's say this is the current state. These are the probabilities that we have, and here we have the alignments. So the sentence here is very minimal one. The house, whose translation is ek ghar, but we just want to know this or generate the correct translation, the house. So these are the possible alignments, and these are the values. So how we compute these alignments is for if we look at this ek and the alignment of ek and the and alignment of ghar and house. So how are we going to compute this is we are going to look at the probabilities that we already have from which are randomly initialized or from the last iteration. So we will use this conditional probability of the given egg. Its probability is zero point 0.7, and we will multiply it with the probability of uh, house given girl. So zero point 0.7 into 0.8, and we get the new alignment probability for this particular alignment of the sentence. Similarly, we will keep on getting updating these values for alignments. So here, the probability of the given egg is 0.7, and then probability of egg given house given egg is 0.05. So the value comes to be 0.035, and we will continue doing it. There is just one step for mathematical benefit is that once we have all possible alignments for the sentence where then what we do is we normalize these values, because if you like count or add these values at this step, they will not sum to 1. So these are just the normalized values of this. Now once we have the probabilities and the counts and the alignment probabilities, we just update the counts. So the probability of the given egg becomes we see here in the alignments the probability of the given egg. So the and egg are here. So the value is 0.824, and also it is here in this alignment possibility egg and the are aligned. So we add it. So all possible alignments, we just sum them up and update the probabilities. And we keep doing this iteratively until we finally converge, or we decide to keep doing it for a certain number of iterations till the values start to not get updated by more than a certain threshold maybe. So you can use different heuristics for that. So this is what we expect to happen at the end of the process of this expectation maximization. So so here you see the edge which is thin, it's supposed to get thinner as we move ahead in in this iterative process, and we expect the model to learn these alignments like born and jump. So just one thing that we have to care about while using this expectation maximization algorithm is if we have to be a bit careful while initializing the probabilities. If we are not careful, we may end up converging to a local minimum. So these are just some basics using these things. So translation probabilities, alignment probabilities, and the way to update these two things, that is EM algorithm. IBM was the first one to introduce them, and they came up with a series of models. So here the first is when I get a sentence there, just to generate a sentence, but there could be infinitely many candidates for it. So yeah. Check infinitely many. Theoretically, yes, but we work with whatever data that is available, right? We are limited by it. So, yeah. So IBM came up with a series of models, each one more complex than the previous one. So there were assumptions like there is a one-to-one mapping, there is a restriction on length in the target language, one word may get mapped to how many words in the target language, and so on. And they use the simpler models to initialize the better models, complex models, and develop their empty systems. If someone is interested, they can get into details of this. So what we discussed so far was at the level of words. So our basic unit here was the word, but actually the SMT systems that perform better are the phrase-based SMT systems, where instead of treating words as the basic units, we treat phrases or segments of the sentences as our basic units. These segments are not necessarily the segments that linguistically make sense. These are just some segments that are statistically important. So advantages of using phrase-based SMT systems are these, that we can sort of memorize the intra-phrase reordering that is required for languages like English and Hindi. So here we have one phrase, the Prime Minister of India, and its translation is Bharat ke Pradhan Mantri. So there is a reordering in the translation of words of these uh, sentences. Now, instead of learning this reordering at the sentence level, we are learning it at the phrase level. And if we can memorize it, then it's easier to perform the translation now. This sort of framework can also help with the sense disambiguation based on the local context. So here, since we are working with much more focused data, we may have a better idea of translating the phrases like uh, this heads towards Pune. Now, what is the sense of head here? Word level SMT model may struggle with finding the translation or correct translation of word head. But since a local context is what that is available, uh, here, even if we have the other phrase heads the committee, it will help us disambiguate it by having their correct translations in the phrase table. Here is one more example. We can learn these phrases in a better way than the word level systems. So here we have a phrase, hung assembly. So assembly is Vidhan Sabha, it's a normal translation of it, but the meaning of hung here is not the literal meaning in this phrase. So there is a specific word for it, Trishanku, so which we can learn if we are operating at the phrase level than at word level. So because of this, since we are making sure that we have confident phrase mappings, we end up increasing overall fluency apart from the overall translation of the system. And actually the phrase, we don't really restrict what would be the length of the phrase. So we may even end up entire system being our phrase and having the entire translation of it in our phrase table. So the goal remains same. Also, we decompose it into language model and translation model. Just the formulation or the modeling of the phrase-based SMD changes slightly. So what we have here is so we have now our sentence not in terms of words but in terms of phrases or segments. Uh, and the translation model of it at the phrase level would look something like this. So as usual, we have the translation probability here at the phrase level, and additionally, we have the distortion model. So distortion model, this in a way learns what sort of reordering needs to be done when generating the text in the other language, because now we are at the phrase levels and phrases may have to be reordered. Yeah. So this is how the phrase tables look after we have learned the probabilities. So here you can see it involves the structure. So a phrase has to be there and there is some parameter learning. So there are probabilities associated with each of these components. So you can see Professor CNR Rao has been mapped to Professor CNR Rao in English, and this constituents a single phrase. So how do we learn them? So simple. So we extend the word level SMT here. So we start with the word alignments and use them to get the phrase level tables. Uh, as I said earlier, so a consecutive words in the sentence form a phrase. But we have to be mindful about what we call a phrase and what we call a phrase pair here. So to call something a phrase pair, the mapping has to be consistent. How do we ensure it? How do we know that this phrase pair is a good quality phrase pair? What we can do here is we can learn the phrase like we can learn source to target and target to source phrase pair tables or like SMT systems. Once we have phrase tables for source to target phrase pairs and target to source phrase pairs, we can simply take an intersection. This is what diagram shows here. If both source to target and target to source give us the same phrase, that means there are no alignments apart from the one which were no other alignments in the target source phrase pair apart from source target phrase pair. We call that phrase as consistent. But if in the other direction, if the alignment is a bit different, we don't consider it as a phrase pair to build the phrase tables. So once we have these phrase pairs, once we have the phrase level mappings and the probabilities associated with them, all we have to do is go to the other side and generate the sentence. Now, how do we do it? So doing this is called as decoding. So we assume we have a huge set, we have a huge space for generation, and we search into that space for further translation, best translation of the given source sentence. So as we discussed earlier as well, just like in case of words, even the phrase table may have phrases which are mapped to multiple phrases in the target language. So that in turn makes it a NP complete search problem and needs some sort of heuristics. So one popular way of doing it is following the beam, like using a beam search mechanism. So we start with empty hypothesis. So nothing has been generated so far. We get possible translations for the first phrase. Here we have 3 beams. We keep our beam size to a certain fixed number. Let's say we are going to look at top 3 translation at each step. So we have 3 beams here and 3 different translations. We get their probabilities. We will get multiple possible choices. Let's say instead of 3, we get 5 different phrases to start the hypothesis. we get the probabilities, or we can have any sort of scoring mechanism to score whatever we have generated so far. And then we rank these hypotheses in our beam. We pick top k. If we are performing beams, if our beam width is size 3, then we take top 3 partial hypotheses and then continue the generation. So at each stage, we are going to end up with multiple hypotheses of size k, and we will get multiple hypotheses, and we are going to select top k using the scoring mechanism we are using, and we keep generating till the entire sentence has been generated. So this is a basic beam search. We can also go for simpler mechanisms like grid search, always picking the topmost phrase pair. But this may not be optimal, because even though at certain time step while generating the translation, at that point a phrase may have a higher probability, but given whatever has been generated so far, it may not be the best candidate. And a phrase with lower probability may be a better candidate to be added to a partial hypothesis which has been generated. So beam search has this advantage that it allows us to scale this process. There is a trade-off as well. More the beams we have, more memory it takes, and the generation becomes slower. So yeah, so that was the decoding, and that finishes our SMT. Uh, Now we will move to NMT. We are not going to spend much time on it. We are going to just touch NMT evaluation and these two other problems. So why do we need a neural machine translation? We saw SMT, we saw if we have data, how we can learn the phrase level, learn these phrase tables, use some decoding algorithm and generate the translations. But then all of this has been there. Why do we need to go for neural approaches? Is because if you look at all these approaches, RBMT, EBMT, like example-based machine translation and statistical machine translation, there is we have no way to represent the similarity between the representations of individual words in the languages. But this is what that neural models allows us. So here is an example of what that means. So if SMT system could translate "I go to school" really well, that doesn't necessarily makes us say that the same system can also translate "I went to college," where just the tense has been changed. But neural networks are seen to do well with such sort of data. Uh, So then what is NMT? NMT is a task of sequence to sequence generation. So this is how it is modeled. So we have a single end-to-end network that we pass a source sentence to it, and it gives us translation in the other language. Unlike SMT, where we had different translation modeling and different language modeling, here we have no such breakings. It's an end-to-end network that takes a sequence, generates some representation of it, goes to the other side and gives a sentence in the target language. So in MT systems use these encoder-decoder network with attention mechanism. Encoder is the component of this network that learns the representation of source sentence, and that representation is used by the decoder to generate the target sentence. And there is something called as attention mechanism, which we will see. Since it is a data-driven approach, we require a large parallel corpus. We will quickly see the recurrent neural network based and transformer based encoder decoder models. So here is a simple recurrent neural network based encoder decoder architecture. We have RNN cells here. RNN networks process the data sequentially. At each time step, we pass a single uh, token or word of the source sentence to the model. The model encodes it, passes that information at the next time step, and we, along with that information from previous time step, we also input the next word, and the model keeps generating or encoding the data that it has seen. Once it is done, we end up with a final representation, which then pass to a decoder, which autoregressively or sequentially generates a single word at a time using this representation. So this vector here is called as the latent space representation of the entire source sentence, or it is also called as the summary vector, which encodes all the information of the source sentence. Again, for decoding, we use any decoding algorithm like majorly beam search to generate one word at a time. Uh, the advantage of using that final representation of the encoder part of recurrent neural network is this. If we if we visualize these vectors in a embedding space, this is what we will look. The sentences which are similar would be closer to each other, and sentences which are not similar would be away from each other. Just like how if word embeddings has been covered, you would know in learned word embeddings, the words which are similar to each other, or the words that fall into a particular domain, are closer than the words that are dissimilar. So, but there are some problems with this sort of network. The problem is we are encoding the entire information of the source sentence into a single vector, which may not be sufficient, especially if we have a very large sentence, long sentence. Since we are processing the data sequentially, the RNA networks may not capture well all the information from the earlier tokens in the type, and our final vector may end up biased towards certain words, especially the ones which came later in the time while generating their representations. So the fixed size single vector to encode entire information is the problem here. Uh, the decoding process is also uses the decoder has nothing but this single vector to help in generating the text in the target language. So that is one more problem. So generation depends on what information has been encoded by the encoder, and that's why we have to be a bit careful about it. Here is something that comes as a solution to this problem. So instead of learning representation of the entire sentence, what we do here is we only while performing the prediction, instead of using that single fixed size vector from the encoder, what we do is we focus on important parts or the words or tokens of the source sentence. So while generating the word jati, I may choose to focus on the word goes than on the word the, to, or school, as shown. So this is what is called as encoder decoder attention mechanism. So this was the original encoder part, that we have RNN cells. We are passing one word at a time, and then we are getting some outputs from each time step. Earlier, what we did was we did not care about these O1, O2, and O3. We only cared about O4. We used O4, we passed it to decoder and asked decoder to give us the entire translation. Instead, what we do here is uh, we now weigh each output of each time step of the RNN encoder cell. So we get these O1, O2, O3 vectors and weigh them. These are called as attention weights, and these vectors could be called as annotation vectors. And then using these attention weights, we finally get a context vector at each time step while predicting a word using a decoder. So these weights A1, A2, A11, A12, and so on, these are learned. We don't fix them. These are learned jointly along with the end-to-end training, end-to-end encoder decoder training. So these vectors here are learnable. So based on learned vectors, we end up with the different context vector at each time step. So this is how it goes for while generating the first word. The attention mechanism focuses on outputs or states at each time step. They are combined using learned weights into a single vector, which is used to generate a word. And as we go on, these weights keeps changing, and new context vectors are learned to generate the translations. So this is at a very high level RNN based encoder decoder mechanism. The problem with this is the sequential processing of information and some limitations that come with it. So after transformer was published, whole shift entire community or field has been shifted to transformers. The advantage here is the transformers are faster. They don't process the data sequentially. Uh, so this is how a transformer architecture typically looks. We have multiple encoder blocks, and collectively it forms the encoder of the neural network. Similarly, we have multiple decoder blocks, which collectively forms the decoder. The final output from the topmost layer of the decoder, topmost decoder block is the final output. Each decoder block uses representation from the top output of the top block of encoder to generate the translations. Now, if I'm saying these don't process data sequentially, how do we make sure or how do we capture the uh, word order information or positional information? Because what we are doing, positions of words and their sequence is important. Let's say I have a sentence, Ram ne Sham ko mara. If I jumble them just because if I don't process them sequentially and randomly and say process it as Ram ne Sham ko mara, I am dealing with a different information here now. So how it is tackled? For that, apart from the usual word embeddings that we always have, what we do is we add additional learned vector. This vector encodes the positional information. So now for each word, we have its embedding, a vector representation of that word, along with additional small vector that denotes the position of that word in the text, which is processed parallelly. So sinusoidal function is used usually to get these positional embeddings for the words. There are other ways as well. The popular one is this one due to its simplicity. Now, if we look into the block of a transformer, this is what it looks like. So we pass all the words which have the word embedding added with the positional embedding for that word, and the vectors of same size are input to a model at once, to the encoder at once. The first layer in this encoder is the self attention layer. The self-attention layer generates representations of the words that are passed by attending to different words in the same sentence. So if I have a sentence for each input X, to generate representation for, it looks at each input token and X and decides which words are important to get a better representation for the word for. And this continues and we get a better representation. This representation is further passed to a layer normalization. Layer normalization allows us to mitigate the uh, standard deviation and the mean of the values that we get in vectors of different word vectors which have been come out of self-attention layer. So this improves the mathematical stability. So once we perform this layer normalization, one important thing here is even while performing the layer normalization, there are certain weights that we learn. So this is parameterized layer normalization that instead of some hard-coded layer normalization. And then we have a simple feed-forward layers to introduce the non-linearity into what we are doing. So feed-forward neural networks is nothing but a simple, fully connected layer where inputs are passed to all neurons and their outputs are passed to next level. So this, and again added with add and normalize, again for normalization, forms the encoder block. Additionally, we have these dotted lines. These are the residual connections or skip connections. These allow us to perform sort of no-op operation. If we don't really want to do anything, if it's sort of identity thing that needs to be done, then these layers allow us to perform it, do it without modifying the data. So this was the encoder block. Now let's go to this self-attention. Uh, so this is how the attention block looks. Attention is performed. So we have the words here. The word vectors are shown here. These could either be the word embeddings if we are at the bottommost encoder block, or if we are in the middle of these encoder blocks in the processing, then the input to the self attention would be the output of the previous encoder block. The sizes are kept always same. So we have either these words or the outputs of previous encoder blocks. So we have one vector for each word. Now, what we do is we use multiple self-attention layers on this information to attend to or to query to different positions in this sentence to learn different information about the same sentence for encoding each word. So the the way researchers looked at it is as a information retrieval task. So here we have three vectors. We have a query, we have a set of keys, and we have values. We want to query the keys and get the correct answer out. So as shown here, we have the multiple inputs or the outputs from the previous layer. And then we have here the learnable weights for queries, keys, and values. These are learnable. So this learning also happens end to end while training the model for the task of our interest, in our case, machine translation. So these learn metrics are multiplied with the word vectors to get the query key and value vectors for the inputs. And once we have this, uh, we perform this operation. We take a dot product of queries and keys, and then we multiply it with the values, the softmax of it, to get the final set of representations, which is set. But since we are dealing with multiple self-attention layers parallelly, we have these multiple Z values from each self-attention layer. So additionally, we have one more parameter or vector or WQ to WO to combine the outputs of all the self-attention layers into a final output. So just the concatenation of the outputs of each self-attention layer is multiplied with this final learned vector or matrix to get the final output. That means final representation for each word. So this is called as multi-head attention. We can parallelly have 8, 12, or whatever number we choose, these many number of self-attention layers in each block. So this was the self-attention block. Now there is a very small change when we go to the decoder. Apart from all the layers that we saw in transformer encoder, we additionally have a cross attention layer, or it is also called as encoder decoder attention layer. In case of self attention, the query keys and values were either the words themselves or the outputs from the previous encoder. But in this case, the query use the information that has come from the layer below it in the decoder, while we for us still the keys are the information that the encoder has given to us. So that's the only change here. One important change here. The other thing is, since we are using decoder to generate something, in case of self-attention, what I said was, if I want to encode the word for, it attends to all other words in the sentence. That means it also looks at the words that come later after for in the sentence. But we don't have this information when we are at the decoder side. Let's say we have generated two words so far. Translation is, let's say, something, uh, मैं बोल रहा हूँ. So let's say I have generated my bowl and I want to generate next word here. I don't have the information about raha and who here, right? So to deal with this, what we do is, while we are here at the attention layer, we mask out the positions which are at the at ahead in the time. So that is called as masked attention. That is one more other difference. and that's it. So yeah, as mentioned here, we only allow the decoder to attend to earlier positions while doing the generation. So this is how the entire transformer looks. So this is the overall network, just a simple representation. And yeah, we train this and the RNN pretty much in the same way. The training is end-to-end. The loss function usually used is the cross entropy. We are not going to get into how we train these models using various strategies that will be covered most probably in DL and NLP course. So now, yeah, so important difference between SMT and NMT was we had different components there. On the neural side, we have end-to-end network. There is no dividing of tasks between tasks while performing the translation. Uh, so now we have seen the SMT system, and we know how a transformer which is used for MT looks like, and it is trained end to end. Let's see now how we can perform the evaluation of MT systems if we have them. How to know that the systems which we have trained are good. So one the best way to perform the evaluation is to go to a human and to perform the evaluation of empty system is to go to human and ask him to tell me how good or bad is the translation given by my system. Uh, this allows us to get really high quality data, but problems as you would come to, you would assume, are this is a slow process and also resource intensive process in terms of again time and money both. But still, if you want to do it, one way to do it is ask the humans to perform something called as direct assessment, where we ask them to score a translation on two parameters: fluency, that means naturalness, and adequacy, that means whether the translation reflects or exactly the same meaning at source or not. On these two parameters, we ask them to rate each translation in the range of whatever range we decide. Usually it is 0 to 100. So we ask them give a number between 0 to 100. 100 means best translation and 0 means poor translation. Or it could be, as shown, it could be a scale of 1 to 5, and it could be separate for both adequacy and fluency. Uh, but as I said, this is a slow process. While we are in the development, even when we train the NMT systems, we look at the blue scores during training. After training the model for X number of epochs, I would like to go and see how better my system is doing. What is the quality of the system so far? That is something that the humans don't allow. One more problem with human evaluation is again, the trustability is again one more issue. One person may be very harsh while evaluating, other could be very lenient. So even though there are some mistakes in the translation, one may give maybe 90 score, the other will give only 20 or 30. So that is something that we have to deal with, and for that we have to go for more human annotators, increasing the costs. So we therefore rely on mostly during development phase, we rely on the automatic evaluation metrics. One of them is before that, there is other study that we can perform using human effort reduction. So this is, we are still at the human evaluation. One way to know how our system is doing to take care of the biases of human is to actually make them sit and correct the translations that our MT system has generated, and then measure the time or measure certain other parameters while they are doing this activity of correcting the translation. Then we benchmark it against the activity of performing the translation using human from scratch. So given an English sentence, we ask someone to translate it into Hindi, but to some other set of human annotators, we give English sentence and the empty generated Hindi sentence, and we ask them to correct it. And then we measure the time difference here, and we say how much effort reduction has been there because of empty system, and that denotes the quality. So as I said, since these things are very costly in terms of resources, so we go for automatic evaluations which are scalable and fast. So two of them are listed here. These are very common and famous evaluation metrics. One is translation edit rate and other is blue. Translation edit rate computes the distance between the empty generated translation and the correct translation in terms of insertion, deletion, shifting, and substitution operations. This distance, more the distance, lower is the quality. So that's a simple way to know how many edits we have to do to reach the reference sentence. So that is what TER is. So it is an error-based metric. The most commonly used and most famous is the BLUE, bilingual evaluation understudy is its long form. So just like TR, this also requires a reference, means correct translation. Uh, so this is one precision-oriented similarity-based metric, uh, and we will just spend some 5 minutes on it. So what BLUE does is, the BLUE metric cares about the n-gram overlap between generated translation, that means hypothesis or candidate, and the reference sentence. And since this is precision based, we go from candidate to translation to see whether the words are present rather than going for recall based thing to check reference to candidate. So here is a quick example. We have one reference sentence and we have a candidate, that means a sentence which empty system has given, let's say. How we compute this score is we compute the n-gram precision. We saw what this n-gram thing is. In 1 gram, so let's go for 1 gram. So here we see we have a candidate. We go word by word since we are at 1 gram. We see whether he is present in reference or not. If yes, the count goes by 1. Then goes word is present. So +1, and we keep on doing this. We would see here that the new word in the candidate is not present in the reference. So we end up with 8 matches. And then we count the number of words in the candidate, not in the reference. So the total number of words in the candidate are 9. So our 1 gram precision in this case is 8 by 9. We repeat this activity for whatever n-gram we want to go till. So most common is to go for 4 grams. The higher n-grams allow us to uh, evaluate the structure of the sentence, while the lower n-grams allow us to cater to faithfulness or adequacy of the sentence, whether all information has mostly been conveyed or not. So that is the reason why we go for higher n-grams. And finally, once we have these values, we simply take a geometric mean. So this is the final score for this translation. So higher is the score, better is the translation. There are some of the problems with the basic geometric mean of n-gram precisions. If we use it, we will face some limitations. The first one is this. Here we have a candidate sentence, he goes to. The reference is same. This is what our empty system gave. Now, if you compute the n-gram precision, since this is precision-oriented metric, we end up getting one score for each n-gram precision, right? So final score is going to be 1. But if you see, this translation is actually a very poor translation and shouldn't get the score of 1. So this is one problem. And to solve it, we add a penalty to it. Okay, so what we do is we check whether the length of candidate is greater than reference. In that case, we are safe because we are this is a precision oriented metric. So if it is more than reference, we don't have to care about it at all. But if it is less than the reference, in that case, we apply this penalty to the overall score that we get. So the score simply changes to the n-gram precision and additionally the brevity penalty. So this is called as brevity penalty. So here with this the penalty would be 0.34, and now you are going to just, so it is going to be a 4th square root of 0.34. So score is reduced drastically from 1. So this was the first problem. The other problem is we may have the multiple reference sentences. Something that we did not discuss so far is the possibility that for same source sentence, there could be multiple correct translations in the target language. Having them is difficult, but if we have it, we should be able to use it to evaluate our system in a better way. We compute the unigrams in a usual way, but if we use the compute the n-gram precedence in usual way, this is what will happen. We have he in candidate. Now, if I get the counts, it will be like he is present once, he is present two, so he word is present two times in the reference. And the length of candidate is 2, so the 1 gram precision becomes 1 in this case. But this is something that we would not like to our metric to do. So we use the clipping. With clipping, we count the occurrence, or we match each word to the maximum number of times it appears in any of the references. So now if we see, the word he appears only once in reference 1 and appears only once in reference 2. So instead of saying the 1 gram precision is 1, now it becomes 0.5 because we count it as 1 than 2. With this modification, now we have solved the problem of multiple references and presence of a word multiple times in different references. But we are not still foolproof. This is still the problem with whatever new metric model we have so far. So let's see this sentence. He watched that film the 100th time. Reference is also he watched that movie the 100th time. The both sentences are same. That says the translation is correct. But since we were operating at the 4 gram precision level, sorry. Film and movie are the only two words which differ in reference and candidate. They are synonyms, so translation is correct. But since we are operating at word level overlap or n-gram overlap, this is what will happen. If you count the 4 gram precision, 4 gram precision will match. He watched that film with 4 grams in the reference. And if you keep sliding the window of 4 tokens, you will see you don't get even a single match. And since it is a geometric mean of 1, 2, 3, and 4 gram precisions and brevity penalty, you are going to this one value 0 is going to bring entire score to 0. So that's why blue is computed at the corpus level. That means we don't use a single sentence or to evaluate empty system. We always have a set of sentences, and the final metric is computed over the entire corpus as opposed to on each candidate. How? So this is what we do. We get the counts of matched n-grams as just using the methodology we just discussed over entire corpus. Let's say if I have 1000 sentences, 1000 candidates, and their corresponding one or multiple references, I get this count for all 1000 sentences, not for individual sentence. And then this count is also summed over all the n-grams, 1 gram, 2 gram, 3 gram, 4 gram. This matched count is divided by the overall count of the candidates, and then brevity penalty remains the same, and this is the final expression that we have. Just the variation of geometric mean using exponential and log here, and this is the final blue score that we get. So this had showed a really high correlation with human judgments when authors ran the experiments. And that's why this is one of the most common metrics. There are some limitations of blue. One thing that even you can think of is, since this is a overlap based metric, like matching based metric, we are not caring about the cases like movie and film, right? So we are not looking at meaning of the sentences, or let's say we are dealing with agglutinative languages like Marathi, where a word could be Ghara Samor Chandi. It is a single word. For its corresponding Hindi translation, Ghar ke samne walo ke liye. So these are separate words. So you can see, so just by adding suffixes to the word encoded all this information. Now it is possible that the empty system makes some mistakes with one of the suffix, but at least the earlier suffixes or the main root word was the correct. This approach does not cater to it is not sensitive to it. It is going to mark the entire whatever generated word with a very minor mistake as not match. So these sort of problems are the limitations of Blue. Apart from other limitations, we are not discussing them now. Yeah, so that was about the evaluation. Now I will very briefly discuss these APE and quality estimation problems. So let's say you have developed the NMT systems or like neural machine translation or statistical MT systems, and you have deployed them. Let's consider the scenario of Google Translate you all have used. They also provide the API. Let's say Google has developed the model and they have deployed it. They are providing access of the model to people through an API. Now you go and translate 10,000 sentences and you come to know that always the translation of number 21, or there is some pattern, like there is some pattern whenever this sort of number comes, these words come, the translations go off. Now how do you handle it? You cannot go to Google and ask them to correct it, or even if they come to know, it is going to take time, and it is also not feasible. Different people will have different needs when on for what activity they are using that empty system, and they would want to adapt the empty system for their application, which is not possible, and that's where this automatic post editing comes. So what we do is we first generate a very small amount of data. Let's say we how do we generate this data? We pass the source sentences to empty system, get the translations. Now we show these source sentences and translations to people and ask them to correct them. Now once they have corrected them, from pairs we have moved to triplets. We have source sentence incorrect, possible incorrect translation, and definitely correct translation. Once we have it, we model the. So we model this problem, we train an end-to-end model for this task and end up with the automatic post-editing system, which is trained in a such a way that it knows how to make important edits to the translation and the entire generation of translation. Quality estimation is something that allows us to uh, quality estimation allows us to get the quality of the translations without having to look at the references, which was a limitation of U and TR like metrics. So maybe we will cover, these are all neural based things. We will cover them along with the final point. Maybe in later lecture or in the DLM.